Moving onward, here is a table we'll fill out that has a apartment whose rent starts at $500 a month. And every year, that monthly rent payment goes up 5%. So let's work on this problem together. So where did we get that $25 from in the first row? We're taking 5%. That would become a 0.05 as a decimal. So we're saying that 500 times 0.05 was the $25. Then we took this number and that number and added them together because we had to add the increase to what we had before. Okay for year one?
Yeah.
In the second year, what do we start with? Well, it's whatever was true at the end of December previous year. So we're starting at 525. We again do a times 0.05. And now we get $26.25. So we'll add that up and we get 551.25, taking how much we were paying and how much more we have to pay next year. So this is what we'll have to do next year. Is year two okay?
Yes.
So same thing. This is now 551.25. It's still 5%, but 5% of a bigger number is a bigger thing. Just like 5% of a millionaire's income is more than 5% of my income. So now we're at $27.56. And we get 578.81. So far, so good.
Yep.
So we could keep doing this. I think that, yes, the answers are there if you want to finish on your own and make sure you got it correct. We could ask what's the end of the sixth year. At the end of the sixth year, what's the rent? We could just say, well, whatever number is in this bottom corner. And the problem is this was really boring. We were just multiplying by 0.05 and adding again and again and again. And a theme that we've seen in Math 25 is whenever you have a pattern, you probably can make it a formula. So let's go back and look at this again. There was this thing we did where instead of multiplying by 0.05, we multiply by 1.05. Do you remember that 1 plus trick from a previous lesson?
I don't remember very well.
So what's happening here is we had an addition step. we had to take the 25 and add it to the 500. We didn't care only about the increase. We wanted to know the combination. So a quicker way to do that is to say that there is a 0.05 from the change, but there's also a times 1. A times 1 would keep the 500 around, so it doesn't disappear and need to be added back on. So if I take that 0.05 change, but just slap a 1 in front of the decimal point, then we get this answer in one step. And check it on your calculator. 500 times 1.05 is 525. So then this becomes much more efficient. So that was 551.25. And that was 578.81. And that's going to be 607.75. $638.14. And 670.05. Yours might be a few cents different because I am not actually rounding on my calculator with each step, just because I'm lazy and don't want to hit more keys. So if you had a few cents difference because you actually rounded when multiplying, then that's perfectly fine. Okay, I want to go back and do something. Now that this was efficient enough, it wasn't a waste of class time to finish. Let's look at these things. What's the rent at the end of the 6th year? We just put a box on it, 670.05. Why does the amount of increase keep changing? So why does this number change from year to year? How would you paraphrase that?
Let's see, because every year it redoes. It's like the 5% increase is like every year, and every year it changes because of the 5%.
Yeah, the thing we're taking 5% of changes, so of course the answer changes.
Yeah.
What's the overall percent change? That's an interesting one. So we're going from 500 to 670.05. So do you remember the percent change formula?
I didn't.
Okay, so it is percent change is change over original. So what's the change? It's going to be the bigger one minus the smaller one. In this case, 170 over. Which of these was the original?
500.
500, right? That was the beginning of our story. So what do we get? 170 over 5 divided by 500 is about 0.34. So that would be 34% after we do our replot. Okay, that's kind of interesting, 34%. Now, we had a 5% change once, twice, 3, 4, 5, 6 times. 6 times 5 is 30. So it makes sense that 30% increase happens because there were 6 5% increases. But where's the other 4 coming from? Why isn't this 30? How did we get up to 34?
I was just thinking the same thing.
You just told me the answer a moment ago. The 5% isn't always 5% of 500. This one is 5% of 525. This one is 5% of 551.25, and so on. So the extra 4% comes from the fact that we're taking 5% of bigger numbers, and this isn't staying 500 the same the whole time.
Okay, that makes sense.
So this is how simple and compound interest are different. Simple interest, this would be 30. We would say that every year you owe the bank $25, or your rent goes up $25, or your bond goes up $25, whatever. And that just happens again and again. We don't reset to bigger numbers each year. It's just 25, 25, 25, 6 times. Compound interest describes what's happening here and what happens in your credit card statement and your bank account. That at the end of a time period, usually monthly in real life, sometimes annually, then all the percentages are based off the new amount. They don't stay fixed to the original amount. So simple interest happens again in a few real life things like bonds and bank certificates of deposits and payday loans. But if you're more used to compound interest, this is why, because in your bank account, on your credit card statement, at the end of the month, that becomes the number that matters. We don't care about what happened earlier in time. All good so far?
Yeah, that's good.
Okay, let's do this one more time. I'm going to copy this whole page. Now, we don't actually care that this amount here is 525. We could just take that and rewrite it as 500 times 1.05, because that's what it is, right? That was the 525. And we don't actually care that this number is 551.25. Instead, we're going to write this whole new line. Do you see why we can replace it with what I'm boxing in with my red highlighter?
Yeah.
Because that's what 551.25 is. So I'm just going to write 500 times 1.05 times the other 1.05. One of them was here and the other was there. And we don't actually care what number this is. It's not our final answer that we want. I can replace that green value of 578.81 with this whole left-hand side. And the pattern keeps going. How many times do we do a times 1.05? It's 1 the first year. The second year, we have 1, 2. The third year, we have 1, 2, 3. The fourth year, we have 1, 2, 3 from the 4, and then 1 more makes 4. Do you see how every year we're having 1 more of those?
Yeah.
Because we're taking whatever we had previously and squishing it into that number. So if we wanted a formula, we could have one. We could say that this number here is going to be 500 times 1.05. How many times? 6 times. We've made it slightly bigger 6 times. The exponent, again, is just shorthand for writing times this, times this, times this, again and again and again. And now that we have a formula, we could do this as much as we want. What if there was year 20? Then we'd say 500 times 1.05 to the 20, and whatever that is. So $1,326.65. We wouldn't have to finish this table for 20 different rows, which is great because who would want to do that? Whatever number we want, we could plug into the exponent and find what the rent would be after that many years. So we have just discovered the compound interest formula. So here it is. The final amount is the principal times 1 plus the percent change, right, the interest rate, with an exponent of how many times the change happens, how many rows we have in the table. And now we just need to do a bunch of example problems. So we start with the 1. We're going to put on a 0.03. Where did I get a 0.03? Because 3% is 0.03 after we screw the decimal twice. And the exponent is 18 months. So I can just put an 18, whoops. Oh, I'm sorry, I forgot the principal times. I'm getting way ahead of myself. More people in class to yell at me. Okay, the principal times the 1.03 exponent 18. So $170.24.
So how it says 18 months, you can just do months for the exponents, or just like how many?
That's a great question. In this case, it said compounded monthly. The payouts happen monthly. So that's the time frame that goes in the exponent.
I see.
If it said compounded yearly, that wouldn't be realistic. Most compound interest is monthly, but it could be compounded yearly. Then we'd have to count years.
Okay.
If it said compounded weekly, again, that usually doesn't happen, but in theory it could. Then we'd have to count weeks here. Something else I want to point out, this formula gives us the final amount. It includes the $100 of loan and $70.24 of interest. Oh, I'm doing this all wrong. I'm sorry. I'm thinking too much about lecturing and not. Let's see, I'm going to just make a big red thing that say, oops, wrong. I'm going to start a different recording with this done correctly. Should I? No, I'll just keep going. Okay, what I did wrong, we don't pay all 3% each month, thank goodness. If your credit card has a 3% annual interest rate, then you don't have to pay all 3% every single month. That's sort of an overall throughout the year thing. So I'm going to just start all over. I'm sorry.
That's okay.
Maybe people will learn it better if I make the mistake, but it's nice if I do it right the first time. Okay, we have to share this 3% among all the months.
Eldar, can I ask a favor?
What?
Pick up all the leaves on the floor and put them back outside.
So if we share the 3% among all 12 months, then that becomes 0.03 divided by 12. Is 0.0025. So it's only that nice small decimal that we pay each month in interest. Otherwise, we would all go broke way too quick with credit cards. Okay, so to do this right, I'm going to say that we have the $100 loan. That's our principal. We multiply that by a 1, and then the 0.0025, and then the exponent is the 18. So what is 100 times 0.0025 exponent 18? So $104.60. There we go. That sounds much more like what 3% compound interest should be. Again, if it was 3% only, it would be $103. So it's slightly more because of the compounding. Okay, let's do a bunch of examples more, especially since I messed up on that one and confused everyone.